This is an acid-base review in terms of equilibrium. We're going to determine pHs, concentrations of H pluses, concentration of OH minus. We'll look at polyprotic acids, weak acids, strong bases, weak bases, salt solutions. I encourage you to pause the video as often as you need to and do the work before you see me do the work. Our first problem is we're going to find the concentration of H plus when a solution has a pH of 11.93. So how do we go about doing this? Well, we know this equation, which is pH equals negative log of H plus. So how do we find H plus? We just flip it. The biggest thing is that most people forget to do the negative pH, and they just do it of pH. So that will just simply be 10 to the negative 11.93. So the concentration of H plus, or hydronium ion, would be 1.17 times 10 to the negative 12th. Okay, what if we have to determine the pH of a 2.8 times 10 to the negative 5th molar solution of HNO3? How do we approach that? Every problem has its own ins and outs and tricks. And in this case, the more you recognize and are familiar with acids and bases, the more that you will understand how to approach this the fastest way. This is a strong acid. One big hint, besides simply memorizing this, is that this has no Ka. So if this has no Ka, then this concentration can be assumed that it's the pure concentration of my H plus. If this is a weak acid, that concentration is not purely H plus because weak acids do not dissociate 100%. Strong acids, we assume that they do. So because of this, being a strong acid problem, life became a lot easier. We take our pH equals negative log concentration of H plus, and we just simply plug it in. And we get a pH of 4.55. So this recognizes that it is a strong acid. You recognize that a strong acid is simply the same as saying the concentration of H plus. Okay, a much larger problem. A 30 milliliter HBr, or hydrobromic acid solution, was determined to be at a pH of 1.25. Determine the pH that results from mixing 80 milliliters of 0.25 molar CaOH2 solution with the HBr solution. Okay, so this is an acid-base mixture. How do I know that? Because this is a strong acid. This is a strong base. All hydroxides in group 1 are strong bases, and then CBS in group 2. So that's calcium, barium, and strontium are in group 2 that make a strong base. So what we need are moles, specifically of H plus and OH minus. So we can then see what we're in excess. Do we have more H plus or more OH minus? Because if we have more than one or the other, then we are going to be able to determine if we're being acidic or in a basic solution. So let's attack one at a time. The hydrobromic acid. The very fact that it tells me it's a pH of 1.25, I need to work with that. So because it's a strong acid and a strong base, I can assume that I'm talking in terms of H plus and OH minus immediately. So I'm going to work with my acid here first, is that I am going to find the concentration of my H plus. So I'm going to take 10 to the negative pH. And that'll give me 5.62 times 10 to the negative second. So now we need to interpret this information. That's the concentration. Sometimes I think it's a good idea to look at molarity and actually use the units that make it up, which are moles and liters. So if we look at it in moles per liter, we can kind of take a look and assess our problem and think, how can we get into the units we want? So we have moles per liter, and right here we have 30 milliliters of our solution. So I'm going to take that and convert it into just moles. The best way I like to do it is actually putting it in the context of the molarity equals moles over liters equation. So if this is molarity, it equals moles over liters. So I have 30 milliliters, so I need 0.030 liters. So this will give me the amount of moles. So that gets me 0.001686 moles of H+. I'm going to start calling it H+ instead of HBr because it is a strong base. Okay, let's take a look. Strong acid. Let's take a look at our bases. So now we have 80 milliliters of 0.25 molarity. So that's actually easier than the last part of our problem that we had with our acid because we already have molarity and we have our volume. So all I need to do is plug it in the same kind of way that I did it with our acid. So I have 0.25 molar. I have 80 milliliters. And I want to find moles of my OH minus. So I have 0.020 moles of OH minus. So I have a considerably larger amount of OH minus than H+. Here is one key element, though. If you saw what I was doing in screaming, this is a mistake. I have CaOH2. You need to remember that this solution, this ionic compound, breaks apart into 3 ions, and they each carry the same molarity. So you can decide to multiply the molarity where each of these are 0.25, and you can treat this like it's 0.50 molarity or molar, or at the ending of it all, the amount of moles I have, I can simply multiply that by 2. So because of that, I don't have 0.020 moles. I have 0.040 moles of OH. So clearly, I have a lot more OH than H+. So one of them is going to consume the other one. You add them up, and every time you add them up, it makes HOH, which is simply water. So I have 0.0383 moles of OH minus in excess. So now that's what is present in my solution. So I can take that now and apply it to the question, which was to determine the pH. So I'm in OH, so now I need to apply pOH, and I need to take negative log of the concentration of my OH minus. So when you look at it then, you need to think about this. This is concentration. So if you rush this too quickly, you're going to make a mistake. Concentration is always moles per liter. So the second part of all mixtures is that you need to utilize the total volume to go back to your molarity. So let's scroll down and finish this up. I have 30 milliliters and 80 milliliters. So I have 110 milliliters of solution. So I need to take that all into account. So I have 0.348 molar OH minus. Now I can use that to plug it into my equation. So I have a pOH of 0.458, which is very low, and it should make sense. I have a lot of OH minus, but I need pH. So reminder, pH plus pOH always equals 14. With a little rounding, we have a final pH of 13.54, which is extremely basic. So, to review on this problem, when you're given acids and bases, you need to make sure you find the moles of your H plus and your OH minus. Then you will take the difference between them to find what is an excess. Then you need to find the total volume and apply that to put your moles of excess back into molarity and then move forward. It would be the same situation if you had excess of H plus. The only difference is that you don't have to worry about subtracting 14 from it then. You'd already be in pH. Here we go. Determine the Kb of a 0.060 molar of Hb, so this is a generic base, when it is determined to be at a pH of 9.44. Wow, a lot of things going on. Well, first off, this tells me that this is a weak base because there's a Kb. Okay, so I'm probably going to need an ice box. I want to organize my information. So let's see where we can put all this information. So if I have my weak base here, I'm going to put this way to the left. All acids and bases, when in trouble or not understanding how to write out the chemical balance equation, react it with water. If you react it with water, H2O, you will have a better understanding of how this works. Okay, so what do bases do? Bases gain H's. Acids give away H's. So another way to think about it is that you will always, if you're in a basic environment, that you're going to have OH minus instead of H3O plus. So sometimes I like to attack the water, and if I know it's acidic, I make H3O plus, because this is a little foreign, HB. I'm not familiar with that because it's generic. So if that's the case, then I must have gained an H here. If I gain an H, it'd become positive. So this is my generic equation. It doesn't really matter what the equation is, as long as I'm tracking my H's correctly. Water is always a liquid, so that doesn't affect my equilibrium expression. So this is where an icebox helps just organize your information. So you're starting with a 0.060 molar solution. So that's going to go there. That's all it's given to me except for pH. So what does that mean? That means at equilibrium. So we'll talk about that in a moment. But I know that these are zeros. So pH deals with the potential of hydronium ion. But pH also has influence from hydroxide ions. So we only have hydroxide. So I'm going to have to determine the pH. Using the pH, I can find out the concentration of OH minus. Here's the other thing. When I'm determining Kb, to find Kb, which would be this expression, let's get this out of the way. I would need to know all three of those concentrations. So that means I need to know the entire equilibrium line. If I'm asking for K, I need to know all these. So my icebox is going to help me using a form of stoichiometry to determine all of these concentrations at equilibrium. So I must know something else at equilibrium. If you're ever stuck with that and you're given a pH and you're not understanding that that is going to go on the equilibrium line. So what can this give me? pH. pH can give me H plus, but pH can also give me POH right away. So that's what I'm going to do first. I'm going to take my 14 and I'm going to subtract 9.44 to get my PO. And it results in 4.56. So what is that? Well, if that's my POH, I can now determine my OH concentration from this relationship. So my OH concentration is 2.75 times 10 to the negative fifth. Where and how do I use that? That's my equilibrium value for OH minus. Okay, well, if you're looking at an icebox, because I have a 0 on this side, it's going to be driven to the right. These are all 1-to-1 ratios, so this would be plus x, and minus x. Well, x is clearly 2.75 times 10 to the negative fifth, because 0 plus x equals that value. So that means that this same value is for my H2B plus. And then on the left side, it'll be 0.06 minus that value. So breaking a few rules of sig figs, I'm going to just show the idea that I am losing a little bit of my value by subtracting a very small number to a much larger number. And these are my amounts. So now all I need to do is plug them into my equilibrium expression, which I've already created before. So let's plug that in. So that would simply look like that. I multiply it through, and I solve for my KB. And I solve for 1.26 times 10 to the negative 8 would be my weak base dissociation constant for this problem. Okay, it says determine the pH of a mixture of 0.250 molar sulfuric acid. Assume first dissociation only. Let's discuss that in a moment. And 1.00 molar CH3COOH, which is acetic acid. And it gives me a K on this one. So, okay, it's a mixture. But this tells me it's a weak acid. There's no K on H2SO4, and based on my knowledge of strong acids and strong bases, I know this is a strong acid. Okay, what does assume first dissociation only? Well, the reason is that it needs to say that is that otherwise you need to account for the fact that H2SO4 is going to dissociate two H pluses, which looks like this. You'll note a couple quick unique things about this. Is the first equation there's a single arrow, and the second one there's a double arrow. The reason why is that a lot of times we write it like that because it signifies that the first equation is not reversible because it's a strong acid. It's completely going to the right. The second one is a weak acid. HSO4 minus is a weak acid, much weaker than a sulfuric acid. So what it's saying when it says assume first dissociation only is that this is the only equation that we're worried about. That's the only H plus that will have significant meaning to our contribution to our pH. So when there's a mixture, we need to track our H pluses. So there's two things you need to always think about. First, you always want to start with the strongest acid, in this case, the largest K. Well, if there's a strong acid, it doesn't even have a K. Technically it does, but it's so large that we don't need it. That's the one we're going to start with. And why are we doing that? Because that will contribute the most H plus. There's a common ion effect that we're going to see in a moment that causes the reaction to shift more aggressively one way or the other as we continue to track our H's, which is the second item that you always want to think about. We're trying to track our H's, and at the ending of our equation, the concentration of H plus is what we're going to use to find our pH. So the first part is the easiest of all this. We are going to utilize the sulfuric acid and see what the concentration of H plus is from this. So looking at the equation, as stated earlier, this will be the only equation we use from the sulfuric acid. So it said that there was 0.250 molar. Now, it looks like I'm setting up an icebox, but because I already know this is a strong acid, there's not a lot I can do with this. But this is why I wanted to show you, is that this is all going to be driven to the other side. Because it's a strong acid, I assume that that's how much I have on the other side. All of it. It goes all to the other side. Well, why am I even writing a note? The reason why is I want to talk about the other equation in terms of this equation. So what do these have in common, and how do we utilize it? Well, first, let's write what we've been given. We were told that the second acid was a 1 molar solution. Terrific. Okay, well, here is the key to this. Is that you have to look above, and there's one commonality. and that's the H plus. So I already have 0.25 molar of my H plus, and I don't have any of my conjugate base there yet. So now I am going to help my cause by using an icebox. Well, where does this go and how is this all used? I need to use my K. I need to use my K value to determine what the value of my X is, so then I can determine the pH ultimately. So let's plug that into that relationship. So that'll be the relationship. I'm feeling pretty good about my initial amounts to my K value. They're well over 100 times greater, so I'm not worried about my 5% validity rule. So I'm able to cross off the X's that are added and subtracted. So now I can just solve for X. And be very careful. X does not, in many problems, X equals the concentration of H plus or OH minus. In this case, X just equals X. And we'll cross that bridge in a moment. So this is my X. Well, why did I say that X doesn't equal H plus? Because H plus equals 0.250 plus X. So that's going to equal, unfortunately, the same exact value because our X is so much smaller. You'd have to go way past our sig figs to have it significantly change it in any way. So sometimes this works, sometimes it doesn't, but you do have to take that into account. So now we just have to finish it up, and we find the pH. Which is 0.602. Very, very acidic. It is sulfuric acid, and there's a lot of it. So that is the pH of this mixture, utilizing two different acid dissociation equations. All right, determine the pH of a 0.5 molar solution of CH3,2NH, and they give us a KB. So the minute I see that, I always think it's probably a weak base. If you're unsure, if you've never seen a formula before, you're going to have to kind of go with your gut on that and realize that it probably is a weak acid or a weak base. Unless if it starts with a metal, then you're dealing with a salt. So we need to have an equation. All bases need to react with water. And again, a base accepts H's and acids release or donate H's. So my water is going to act like my acid. So here's a little extra exercise. What if I asked to label my acid and base, conjugate acid and conjugate base? What would those look like? Well, if this is my base, and this automatically has to be my acid, its partner would be its conjugate base, and this means that this would be its conjugate acid, right? Okay, let's look at this in terms of an icebox again. So I have point 0.5 molar, and that is all that I've been given. So if you've been doing this enough, you will recognize that this is x squared over initial minus x equaling your k. If you need your icebox to give you extra information, use it. But ultimately, that is where we're going to end up. So there it is. So X is going to equal my OH minus concentration, and that will be 0.0172 molar. Now, if you're sitting here wondering, is this okay? Was it okay to cross off my X? I feel that it's clearly 100 times greater. Well, we can always just check it. And how you do that is you take your X over your initial, and it needs to be less than 5%. So I can do that right now. I'll take my final, my X, over my initial, and if I do that, I get 3.4%. That is less than 5%. So it is okay. It is valid that I can cross off that X. It doesn't affect my answer greatly. So now I can finish this up like we've been doing during the entire review. I want pH. So I'm going to plug in my POH. Which is 1.76. I take 14. I subtract the 1.76. And I get a final answer of 12.24 for my pH, which is basic. Okay, determine the Ka of a 0.5 molar solution when 23.5% ionizes. Okay, some of this terminology can be confusing. So I need to find Ka. So we had a previous problem about this. Once I run into a problem that says determine the Ka, that means in my ice box, I need to have all of my equilibrium values already known. Now, this says nothing about what solution this is, what's the identity, but this is a weak acid. So because it's a weak acid, let's call it HA. It's generic. So an HA will dissociate into H plus and A minus. Okay? So this is all we know right now, that we have 0.5 molar of HA. Whenever we only have an initial, that means we have zeros for the others. So what does 23.5% ionized mean? It means that that's the percentage that it will turn into ions, which are those two, H plus and A minus. So what we need to do, and I'm just going to do it on the side to show, is we need to find out what is 23.5%. So if I have 0.5 and I multiply that by 0.235, I get 0.118 molar, meaning that's the concentration that has broken off as ions at equilibrium. So I'm going to plug those two values in on the equilibrium line for my two ions. Well, because there's zeros here, it drives to the right, so this is plus x and plus x. So right there, that's x. This equals x. So when I subtract that, what I want is 0.5. This is what it's going to be, 0.500 minus 0.118 for my value there. And that results in 0.382 molar. So I have my entire equilibrium line. And because of that, now I can plug that into my K value. So my K expression of my generic acid, if asked of me, would be this, which then results in this relationship. Calculated out, we get a Ka of 3.65 times 10 to the negative second. Okay, determine the amount of 0.8 molar HCl is needed to neutralize 125 milliliters of 2.5 molar NaOH. Keyword, neutralize. This does not need to be that tricky. To neutralize, that means I need the same number of moles of acid equaling my base. Moles are the amount of stuff you have, so you need the same amount to equal out. If it equals out, H plus plus OH minus makes water, and now we're neutral. So I'm given a molarity. I want to know an amount. That's translation to say volume. I have another volume, and I have a molarity. So this is MAVA equals MBVB. You learn it initially as M1V1 equals M2V2, but putting the A's and the B's just direct you to the acids and the bases a little easier. So all we need to do is plug this in. Liters, milliliters, it doesn't matter unless it's being asked, because units will cancel out from one side to the other. It shouldn't be a surprise that the value is a lot larger than the volume of the base, because the concentration of the base is extremely high in comparison to the acid. So you're going to need a lot of acid to neutralize the 125 milliliters of the NaOH. Two more problems. Determine the pH of a 0.2 molar NaHBr NaH4 Br solution. Excuse me. And then they give you a Kb of NH3, 1.8 times 10 negative fifth. Okay, so this can be very confusing. They give you a Kb of a substance that doesn't quite look like the formula that they give you. So that should actually hint you towards something. That this is a salt. And normally salts start with a metal. This is a polyatomic ion, ammonium. So you need to figure out what the equation is. I'll tell you this, that they always will give you the K value of the conjugate partner of the ion that you need. So this salt is going to break up into NH4 plus and Br minus. One of those is going to react with water to create an environment that we can determine pH from. Now, there are many, many ways to do this. But here's a little bit of a cheat. You just add OH, because OH minus would attach to the plus. And if you add H to that one, what that will tell you is what this solution is going to be, acidic or basic. Well, this right here is a weak base, and this is a strong acid. So because I say that's a strong acid, I know this is going to be acidic. So that's kind of how I like to approach it. So if you always think about water reacting, if it was in a basic solution, water would turn into OH minus. If it was in an acidic solution, it would turn to H3O plus. Well, I am saying it's in an acidic solution. Here's another thing I know, though, is that whatever K they give me, I do need to utilize that. So if it's of NH3, that's a partner of that ion. So I need to utilize the NH3 and the NH4 plus. Well, how to make this work is that the water looks like it has gained an H. Well, the only way it's going to gain an H using the NH3 and the NH4 plus is that if I start with NH4 plus, so it can take away that H to create my NH3. So that is my equation. And you can start an icebox, and you can plug this in. But very quickly, you're going to notice that this, again, is an x squared over initial minus x. The bigger concern that we have is how do we end this? You can't use a Kb when talking about an acidic solution. So we need a Ka. So reminder, Ka times Kb equals 1 times 10 to the negative 14th, which comes from the dissociation of water at 25 degrees. So I need to determine my Kb. Excuse me, my Ka. So my Ka is 5.56 times 10 to the negative 10th. So it's going to be x squared over 0.2 minus x equaling my Ka. X is going to be equaling my H plus. And I get 1.05 times 10 to the negative fifth. And then I take this home, solving for pH. Which results in 4.98 as the final pH of this salt solution. Okay, final problem. It says determine the pH of a 0.1 molar H3ASO4 solution. And then they give you 3 K values. So what this tells me is that this is going to dissociate 3 separate times. So this is a lot like the mixture problem, except this is a polyprotic acid, specifically a triprotic acid. It has 3 H's. And what we need to do is we need to keep track of our H concentration. So I'm going to go through each of these dissociations and show you how we track this. So this is our final problem of our review. So the first one we have is always the simplest. This is just pretty straightforward based on how we do ice boxes and how we calculate our X values. But let's take a look at the first one. So it says that I have a 0.1 molar solution. So that's what I have to start with. I need to make it equal to my first K. So here's my first K. Cross out the X. And I get 0.024495, and I'm keeping all the digits for now. When I do a longer problem where I know I'm having to track values, I'd rather keep more digits and cut them off later. Here's my concern. I have 0.1 as my initial, and my K is times 10 negative third. So times 10 negative 1 times 10 negative third, that's borderline times 100 times greater. So what I want to do quickly is just check this out. Is this 5%? And obviously, dividing by 0.1, it's not going to be 24%. That's not good. So what we need to do is we need a quadratic equation. So we need to get our terms into an ax squared plus bx plus c equals 0 relationship. So we need to expand our expression, and this is my calculation. Get x squared plus 6.0 times 10 to the negative third minus 6.0 times 10 to the negative fourth, and that will equal 0. So now I need to plug that into my negative b plus or minus b squared minus 4ac square root over 2a. And you always get 2 values, and the value that works and makes sense is 0.0217. Now, if this was just asked what is the pH after the first dissociation, you take negative log of that and you'd be done. But there's more to it. There's another whole dissociation. So the second acid results from being produced in the first reaction. Keep track of your charges. I've lost another H. So now it's going to be a 2 minus. Take a look on your left and your right. You have a negative 1 on the left, and you have a plus on the right with a negative 2. Well, that results in an overall charge of a negative 1, so that's still balanced. Let's take a look at our icebox now. This is where it starts to get a little more complicated. So what you need to understand is that your x's right there equals that x. So those are going to be tracked, and they're going to fall down onto the next equation. So I have this concentration for my H+, and I have this concentration for my weak acid there, and I don't have anything for my ion on the other side. So now my icebox becomes more important because I need to organize my information. So now I'm going to plug this into the second dissociation. which will look a lot like this. I'm going to use my second K value because it's the second H that is being dissociated off. As I continue, my Ks will always have a smaller value, so I start to be safe in dodging my quadratic needs, and we can always double check that for sure, but this is always a unique situation because you have equal amounts that you start with on one side and the other. So when you start to cross off some things, you can cross off your x's that are being subtracted, and mathematically, these are going to cancel. So your x actually ends up equaling your conjugate base. This is a unique situation because this is where you kind of have your half equivalence point, where you have equal amounts of your acid and your base in the beginning. So your x is going to be 1.05 times 10 to the negative 7th in this situation. I'm only boxing this so I don't lose sight of what I see. Here is the unique part of this, is that this is now not just x any longer. It has another value plus x. So when we take that into account, it's going to add up. We are tracking our h's to our final dissociation. So I take my final weak acid that was produced. It's going to break into another H plus, and then an ion. So now we still need to track this. So this is very important to see that I have an x right here. Well, that x equals this x, 1.05 times 10 to the negative 7th. So I need to plug that in for this value on the left. But the x on the right, the h on the right, that is 0.0217 plus my x from the dissociation. So I need to add those up if it affects the number at all. But because the x is so small, it really doesn't. So it's still just 0.0217. And then I have 0 for the arsenate ion. So now I finish off my ice box like I have before. Because it didn't affect my H, I fear that it may not affect my H plus again, because my third K, which should be a negative, apologize, will even be smaller. So let's take a look at this last problem right here. So I'm going to, again, make this all equal to my K values. I'm going to cross out my x's, and I determine that x is going to equal, it's going to equal 1.45 times 10 to the negative 17. So this is very small. So this isn't really going to add to my H plus, but it shows you what you would need to do. My H plus would be 0.0217 plus that value. Well, that, again, isn't going to really affect it. So now I can just kind of finish calculating this out. So my pH is going to be negative log of 0.0217. And my pH would be 1.66. So this problem could have told you that all of the concentration of H plus comes from the first dissociation, but I wanted to make sure that you understood how we could track the H pluses as we go. So that concludes this review of acids